So this workshop, it's called very broadly, Introduction to Parallelism and Supercomputing Workflows. And that's a very grand sounding name for what I hope is a fairly general workshop, where our goal is just to go over some of the concepts that Chris introduced in the supercomputing training on Wednesday, and to just give you a general indication of the sorts of considerations you should be keeping in mind when you're trying to figure out how to, efficiently use your allocation, whether that be a Nimbus instance, GPUs on Topaz, or thousands of CPUs on Sotonix. And I know it might be some of you here who have some experience already working on one of Pawsey systems, and I know Emily, you are an active researcher on Pawsey systems as well. So if anyone has something they would like to add that they think is helpful, encourage you to chime in. And in addition, please ask questions, because I'm happy to do my best at digging into anything a little more if you're curious. So I've shared the website that we'll be using for this session in the chat, trialing a sort of a new format for presenting the workshop content. So thanks for bearing with us as we're, run this, I guess, beta format. Hi, David. Just mention as well, of course, David has used Pawsey systems for research and works professionally in HPC. So it's another great resource when it comes to thinking about parallelism. And yeah, David, feel free to chime in as we go through this discussion. Awesome. Great. Just a second. Got to let the dog out. Perils of working at home. Okay, so we're going to start off by talking about parallel computing. And where pretty much all of us will be here because we're working on some sort of project that can take advantage of parallel computing. And that is a type of computation where we carry out many calculations or processes in general simultaneously. And we do that by breaking some larger problem into many smaller ones that can be solved independently at the same time. And parallel computing is deeply intertwined with high performance computing and supercomputing. In fact, I'd say you can't really have high performance computing without parallel algorithms and parallel workflows. Now, it's important to note, and we'll be discussing this a little further, that parallelism is distinct from concurrent computing. So concurrent computing involves switching between processes, whereas parallelism is genuinely working on different processes simultaneously. And the reason why we're interested in this is because for hard tasks, research tasks in particular, it can speed up our work by tens, hundreds, or thousands of times, and essentially, make unfeasible workflows and workloads feasible. And the reason we arrived at this paradigm is that, well, in the mid-1960s, Gordon Moore, he predicted from only 3 data points that the semiconductor density on processors would double every 18 months. And quite amazingly, given the small amount of data, this prediction held true. It's an interesting question, though, to consider whether or not it was a predictive or how much it drove the market. But either way, it's still quite impressive. But more recently, we've come up against limits. In particular, as the size of these, as the density of the semiconductors increases, we run into design issues controlling the flow of electricity through these chips. And we also encounter much higher power consumption. So essentially, the power it takes to run these processors with denser semiconductors, that increases at a faster rate than the increase in computational power. So these two processes sort of, aligned, and to solve that, CPU manufacturers started to place multiple simpler processors, or what we would call CPU cores, on the one sort of greater, I guess, like CPU die. Now, this gives us extra compute performance, right? If we have like a 3 gigahertz core and another 3 gigahertz core, well, in theory, we can get like 6 gigahertz worth of clock cycles per second. But there is a reason why we don't just hear about parallel computing in every context. And that's because, they typically, to implement a parallel algorithm or data processing pipeline, it typically takes more time, as in like human time to implement. And they're, in general, much more complex at some level, and therefore harder to debug. And even when you sort that out, they usually require more time to maintain. So for like a one-off task that's quite intense, it might be just more efficient to like leave your computer running overnight. But for computational research tasks, we're rarely performing a one-off operation. And in instances where we are, the scale of the problem is just so large that we can't reasonably run it on a laptop for weeks and weeks and weeks. And there are, so just to mention some of the types of parallelism. Now, there's actually quite a few, depending on how you want to frame the idea of parallelism in computing. Something that I find amusing, because I'm a bit of a geek when it comes to all of this, is you could see like moving from an 8-bit computer to a 16-bit computer as actually being a type of parallelism, right? Because if you had a 16-bit computer on an 8-bit computer, it'll take maybe roughly twice as many, maybe more operations to crunch that. As you move to a higher bit system, that speeds up. But we don't really have to think about that sort of thing in our day-to-day work. As a researcher working on a Nimbus instance or one of Pawsey's supercomputers, you'll be encountering two sort of modes of parallelism. One of them is data parallelism, where we have multiple processes executing at the same time on different chunks of a data set. And then there's task parallelism, where we've got multiple processes executing different instructions on either the same data set or different but related data sets. Now, I mentioned earlier that concurrency is not parallelism, and I think it's a very important thing to appreciate. So like concurrency, that's the idea that we can progress on more than one task over a period of time by switching between other tasks. So that could be checking your phone while studying, taking turns in a game of chess, or having one CPU switch between different instructions related to different programs. In all of these scenarios, no task is actually occurring simultaneously or at the same time. It's just merely that, if we switch fast enough, it'll appear like we're processing simultaneously. But if you just keep on adding tasks that you have to switch between, everything will eventually grind to a halt. If you remember working on your old laptop from maybe 5 years ago or so, where it was pretty typical to have just maybe 2 cores or 1 core if you were unlucky, your laptop, once you've opened about 10 Chrome tabs and you have your music playing and a video, you start to see everything kind of grind to a molasses sort of crawl, as that illusion of simultaneity is broken. Now, parallelism, like I said, it's splitting a task into smaller subtasks that progress independently. So this could be, writing the introduction to your thesis or an article while your numerical simulations are running. Be running heats in a chess tournament. So instead of having each pair face off one after the other, you have the semifinals, finals, and final. Or could be 2 CPUs searching through halves of a data set to find a maximum value. And that's really important, right? Because this actually reduces the time taken to solve a problem. But it comes with a couple of caveats. These parallel processes will often need to come together to share information. So, that could be in the chess case, right? It's deciding, who will move on to the next heat. So who won that round? And in the case of that search for a maximum value, at some point we will need to bring all of those, we'll bring both CPUs together and actually, find out which CPU has found the maximum. So we'll have to compare values between the CPUs. So there's this additional layer, right, of parallel logic that we often have to consider. I think I'll just take a moment here to see if anyone has any questions, or if David and Emily, is there anything you'd like to add we've spoken about so far? I can't actually see the chat, so, but great. I'm just going to take that stunned silence as all good then. Great. So, a few useful, there we go. Aidan. Yes, so in task parallelism, it could be completely different data. So, like, if you viewed, right, 2 jobs submitted onto a Pawsey cluster, right, as sort of being related in that they are jobs running on a Pawsey cluster, in a sense, right, that's kind of task parallelism. More generally, right, you could actually have, like 2 different data sets that are related to your problem, but maybe a different format. Maybe they need to go through a different pipeline, and they could be running in parallel. Yes, and there's single instruction, multiple device. We'll touch on that as sort of distributed memory parallelism, I think, in a little. It's the broad way. I think we'll think of that. Multiple data. Thanks. Yeah. Do you want to speak on that, David?
I mean, there's not too much to add on that, but there is this concept of SIMD, where on the physical processor itself, you have these instructions where if you align the data correctly, and you can align data from multiple tasks correctly, you can apply one instruction to the whole data all at once, which is very cool very, very difficult to program, but probably the most efficient way to use the silicon.
Exactly. Like you might hear people talk about vectorization, and that's a mode for achieving this single instructions, multiple data operation.
Like if you hear any of the rage over this APX 512 instruction sets, that just means you have a vector of length 512, and you can apply a single instruction to it in one clock cycle. And so if you align your data right, you can maybe have two tasks, put in their stuffs into that 512-bit vector and do it all at once, which is really cool.
Pretty exciting if you have a project where you're spending a lot of time working in very dense C++ code, doing low-level optimizations. But if you see those terms out in the wild, that's why people are excited. And sort of in that vein, put together a list of a few useful terms. It's good to just have these floating around in your mind in case someone brings them up. For instance, right, there's a thread. So thread usually refers to a subtask in a parallel program or pipeline, and that's different from a CPU thread. So often we'd be talking about a parallel process that's actually associated with a physical processor. So that could be a core in a CPU or a compute core in a GPU. And then there are sort of different modes for writing parallel programs or developing parallel pipelines. So they are shared memory parallelism. So that's a parallel process where threads share the same memory or like RAM. And that includes, so that means that they share like the same data and variables and so on. And then there's distributed memory parallelism, where we have a parallel process where all of the threads have their own memory. So they don't actually share the same variables or data. So you could kind of think of distributed memory parallelism as separate programs running on separate computers, and they only communicate if we explicitly tell them to. You'll encounter shared memory parallelism more working on a workstation, your own laptop, or a Nimbus instance. And then, but distributed memory parallelism is basically like the main mode of really kind of getting an advantage out of a supercomputer like Photonics or Topaz, with a few caveats there actually, which we'll get to. Then we have synchronization. So that's referring to the point at which threads come together to access objects or data that other threads have operated on. So this could be shared variables like a running total. And the reason we have synchronization is to prevent race conditions. So a race condition is an unexpected result or behavior due to some sort of fault in our parallel logic, where the process is making some sort of decision based on a variable or data that like not all threads have updated. So in that earlier example, where we had two CPUs looking for the maximum value, if they didn't synchronize, so come together to find the true maximum, we would wind up with two processes with each having a unique value for the maximum, and then potentially making completely different choices further down the chain. And because in a parallel process, if everything is truly running simultaneously, we can't rely on any set order. So race conditions can be quite nasty and hard to debug. On the other hand, because of synchronization and a few other factors that we just simply can't work around, we also can encounter parallel slowdown. So just because we've introduced parallelism, it doesn't mean we'll get a speed up. We have to ensure that there's enough work, for instance, for each processor, such that, the overhead that we incur from having to, start and set up these parallel processes, is offset, right, by the amount of time each process spends working independently. So, unfortunately, as we add more and more processes, it's typically the case that they spend more and more time on inter-thread communication, and eventually you'll start to see a decrease in performance. And finally, you'll probably encounter the idea of fine-grained, coarse-grained, and embarrassing parallelism. So fine-grained, we're talking about a process where all of the threads have to come together to communicate, synchronize frequently. Coarse-grained, we're talking about some sort of process where the threads infrequently communicate, so a few times a second, which is a long time for a computer. And then there's embarrassing, which is just the best case scenario. So in that instance, we have threads communicating rarely or not at all. And ideally, in an ideal world, all of our tasks would actually be embarrassing. But this isn't actually, the case. However, I would just really emphasize, right? Embarrassing, it's threads communicating rarely or not at all. So sometimes they're easy to miss when you start out computing because they just seem so simple or obvious. For instance, just running 100 copies of my program with different input data. Okay? That's an example of an embarrassingly parallel approach to a problem. So it's good to think whether or not you can take advantage of that. And finally, for this part of our discussion, I just want to touch on some parallel APIs and frameworks. Some programming language support parallelism out of the box. Just a few here. We've got Julia, co-array Fortran, on C#. They all support either shared memory or distributed parallelism. And in addition, we also have quite a few different parallel APIs. So that's application programming interfaces. And they include CUDA, OpenMP, and MPI. Note that OpenMP and OpenMPI are two very different frameworks for parallelism. And I think as Chris discussed yesterday, on something like Cetonics, you're likely to encounter, CUDA, OpenMP, and NPI. So CUDA is a framework for writing parallel code on GPUs, where the thing is, the GPUs, right, they were designed for rendering computer graphics, which is basically performing a bunch of matrix operations in parallel. And as a result, they have hundreds or thousands of these very simple processing cores to carry out these operations. Whereas in OpenMP, that's designed for CPUs. So you have multiple cores that can work in parallel. And the upside is a CPU tends to be a little more sophisticated than a GPU core, but as a result, we have fewer of them. And then MPI, so that's really, if we want to do shared memory parallelism. So that idea where we have multiple programs, say running on different nodes, and then they pass messages between each other only when we need them to. Now, if you're not actually writing, parallel code explicitly, which is going to be the case for most people because, we're researchers from a bunch of different disciplines, not necessarily software developers or computer scientists, just know that you will be using something that is taking advantage of parallelism. And that'll generally be through a software library that other people have developed to solve a lot of these issues. And like these include things like NumPy, which actually has some shared memory parallelism built in, or the Intel math kernel libraries. So we talked earlier about vectorization. So these libraries will be highly optimized to take advantage of things like vectorization on Intel CPUs, or machine learning frameworks like TensorFlow or PyTorch, which are a Python front end to CUDA libraries that can run very, very, very efficiently on GPUs. And what you'll be using will really just depend on the system that you have access to, and also the task at hand. So everybody's project is unique in some way. So I see, Carl, what is the difference between CPU threads and process threads? So here, sort of using the term process or processor to refer sort of more generally to a processor that's present on a GPU or a CPU or some other device, but really those are the two sort of devices we need to think about. So, it's not really correct to talk about CPU processors on a GPU, but but both of these systems are like, they contain cores or processors that can carry out numerical, mathematical computations and logical computations to run a program. So it's just a more general way to refer to it. David, do like to add to that?
Yeah, I think that there really needs to be an important distinction need to be made between a process and a thread. And I think it's most useful to look at processes and threads at the operating system level. A process is its own contained little thing, like it has a UID, it has, its own segment of memory, and it has its own set of, allocations and properties to be put on with the scheduler. And that means that it can run by itself on a core independently. And it's by itself. Whereas a thread is kind of like the property of an existing process. It's, processes have threads. And so a single process, its own self-contained block of software, has threads that can do computation for it. And what that means is, when we say what's the difference between CPU threads and process threads, is that there's only one key difference that really makes perhaps the greatest advantage of a thread is that it has shared memory. Because it's that single process that has its own block of memory, all the threads can read back to that memory and look at it whenever they want, however they want. But when you have multiple processes, it means that the processes can't look at other processes' memory. They have to communicate between each other, and that's normally pretty hard. And so the greatest advantage of a thread is that shared memory, but the greatest hindrance is also that shared memory, because you have to read it in certain ways. With processes, their greatest advantage is their isolation and the ability to be shipped out onto whatever core, but their greatest disadvantage is the fact that they have that encapsulated memory and they can't communicate well. So it's a bit of an interesting time. And as Edric said, the concept of a thread on a CPU is quite different to it's different to the concept of a thread on a GPU. When we think of a thread on a CPU, we kind of think of something that's processed like it, will execute instructions, has permissions, and it's like a single thing. Whereas a thread on a GPU is normally associated as part of a thread block that is run massively in parallel. Like on a CPU, you might only have 32 threads for a 16-core chip, because they're running in whatever SMT mode or whatever. But on a GPU, you might have thousands of threads because they're being run through these parallel pipelines. And so as Edric said, you want to think of CPU and GPU threads very differently, but you also want to think that a thread is not a process, but they do work together. Does that answer your question, Carl, at all?
Yeah, that was it was I understood that threads are well, you can run threads from within a process, but like when it was just stated that CPU threads separately, but yeah, I get it. Thanks.
Yeah. So
It's
also,
there's different.
yeah.
Oh, sorry, David.
One last thing is that there's a slight difference between software threads and hardware threads, which
I
you
think
might,
we should focus
yeah, that's
on
probably a bit
hardware.
too hard.
Yeah. So that's the
That's pretty
you hit
much.
exactly on the difficulty in discussing this, because if there's like threads as well and processes, right? How you might talk about them from the standpoint of algorithm design. So it's really that the distinction we're making is that shared memory or non-shared memory. And you know, when you're developing your algorithm, you might not be thinking about a physical device. This is sort of just an abstract. But then when we get to an actual device, then we have similar terminology, such as like, you know, the software threading and so on. And all of it is its own sort of subject in its own right. And it's like all pretty interesting. But loosely speaking, it's good to think of like a one-to-one correspondence between every one of your parallel processors and threads, and then some physical processor on your device as just a starting point when you're getting into this stuff. Do you think that's a fair way to look at it, David?
Yeah, pretty much. I suppose the key takeaway would be that just because you create a thread in your programming language doesn't mean that that's going to be a thread on a core on a machine.
Yeah, that's something you need to be careful of, you know, or you know, think about when you're making your allocation request, which we'll get to. Awesome. So Aidan asks, you know, for embarrassingly parallel tasks, so should you then instead use a type of thread that cannot really communicate instead of threads that can communicate well? What would that look like? Different CPU threads. So it's a great question. So if you have an embarrassingly parallel task, oftentimes you can use a distributed memory, you know, like framework, and you know, just run that, right? Either on a local machine or then scale that up to a cluster, because you don't really have to worry about the processors being able to share memory. And although those programming frameworks can actually be a little more time consuming to set up, if you were, you know, implementing some algorithm with communication, they're actually fairly straightforward if all you need to do is spin up a bunch of duplicated tasks and, you know, access some sort of chunked memory. So yeah, it does, you know, change how you might want to, you know, approach the program programmatically. Yeah, it's a great question. So C#, oh sorry, C++, it, I can't really speak to the you know, the most up-to-date support for shared memory parallelism, because I know that there's some interesting work going on, like just like the C++ standard. However, I would say that basically C++, C, Fortran, and most compiled languages support OpenMP, which is a, you know, a mode of kind of adding, altering your code in this sort of flexible way, where your then compiler can basically identify that you're asking, hey, for this loop, I'd like you to parallelize it. So in that sense, there's support usually for shared memory parallelism out of the box. For distributed memory parallelism, we would need to use some other framework, and that framework would typically be MPI.
Yeah, so just to add on to that, so short answer to the shortest answer to your question is no. It doesn't support. You have to rely on some kind of library, unless you're willing to work with operating system threads directly. C++ 17 added a number of algorithms which are thread safe in the standard library if you're lucky enough to be working on a project that's that standard compliant. But otherwise, generally the base programming language spec of these older languages didn't have this kind of massive parallelism in mind. So for threading, it's often, as Edric said, easy to go to OpenMP or MPI. Java does have some extras, parallelism support, and Python does the thing as well. But yeah. So the short answer is the programming language itself can't really do threads. It has to communicate with the operating system to get resources. So whatever way you look at it, if you're trying to be parallel with hardware, it's about how the software interfaces with that parallel hardware. Some pieces of software do that better and in more user-friendly ways than others, like Julia, and other ones like C and C++, you have to work a bit harder because it is really an operating systems level concept as opposed to a programming language design concept. The concept of threads, but parallelism is like modern algorithmic concept.
So I think to add to that, it's it's interesting, right, that like C, C++, and Fortran are sort of the standard languages on high performance computing and in distributed computing. Like if you really kind of dig down to whatever library it is you're using, and that is really because of libraries like OpenMP and MPI, which are developed by these separate standards bodies and are designed to be very portable. So you can kind of use MPI, write MPI code, or insert you can write MPI code or insert OpenMP directives, is what we would call them, into your code, and then compile it on pretty much any system. So while the base languages themselves don't really have that support, they run fast, they compile to efficient code, and we've got these, very mature and portable standards. So it's even like the sort of newer inbuilt sort of language specific support from Julia or even like Fortran CoArray, like the adoption is like quite slow because the HPC space is like very much in a paradigm where these portable frameworks are kind of supported. So I suppose one thing to mention is it kind of means that, like, is it hard to write parallel code in C++, C, or Fortran? Not really. You can get up and running and writing parallel code within, a minute on most Linux machines, I would say. A lot of the time, the software you need will be installed. Is it easy to write that code? No. Or sometimes maybe, but the barrier to actually starting that process is low. Cool. So just to speak a little bit more on how we can use supercomputers efficiently. And a lot of this advice, applies to some, to your own machine or a workstation or a Nimbus instance as well. But we'll be focusing on supercomputers in particular. And we mentioned earlier that we can't just like keep on adding parallel processors because there's usually an associated overhead. And it's also the case that really there's always some fraction of the total program or process that is inherently sequential. So that's, some point where we need to, synchronize all of our parallel processes or threads. There's a very well-known equation in parallel computing called Amhabdal's law, which basically predicts that if we have a problem of a fixed size, the proportional improvement will diminish as we increase the number of parallel processes. So what that looks like, it's something like this curve here, where for this particular parallel task, we start off, with one core, and then the speed up. So that's like the wall time, single core divided by the wall time or the run time, of however many cores it is you're using. It starts to increase pretty rapidly at the start, and then eventually it kind of plateaus as we hit this asymptotic kind of convergence to the maximum possible speed up. And that speed up, that'll be proportional to how much of your process is actually kind of parallel. So if you're in a position where you need to develop like a parallel data processing pipeline or parallel code, it's really great to just get a pen and paper out and start to try to really kind of figure out how you can reduce that process communication as much as possible. In addition, we have to think about data latency, also bandwidth, but we'll just think on latency here, and how that can be a bottleneck to your process. So I'm going to try drawing here, see how it goes. So in very, very broad terms, you can think of when you're working on a computer, right? We've got our CPU, and it consists of some number of CPU cores. And these are the cores that are responsible for carrying out all of the logical operations that we need to run anything on our computer. And our cores, they have access to some memory that will be on the same die, which we refer to as the cache. And the cache is this like ultra fast memory that the cores have super fast access to, but it's quite limited because we can only fit so much of it on a CPU die without the cost just ballooning. So if we're running a program, what happens is the CPU broadly is sending requests across this sort of communication pathway that we, it's called the PCI bus. So it sends a request to this, and then is fetching memory. So this is data that we need to run our simulation instructions for all of the programs we're running. Takes that from memory, which typically refers to RAM. So that's volatile memory, that we use to store memory for currently running programs, processes. Now, to get data into our memory, we need to load that off some sort of disk drive typically. So we've got it'll be often a solid state drive, or maybe a spinning hard disk drive. And just to be, the PCI bus comes into this as well when it comes to the data transfer. But just know that really it's, first port of call has to be moved first to our memory or RAM before the CPU can start loading it into cache to do anything. Now, if you're on a system like Topaz, we'll also have a GPU. Yes. Thanks, Aiden. SSD. Now, if we're on something like Topaz or a Nimbus instance with a GPU, we'll have our, graphics card, at least one. And, it's important to note that the GPU actually consists of its own collection, as we've discussed earlier, of cores, typically many more than you would have on, well, always many more than you would have on a CPU. And that, simply put, these cores will be accessing data and instructions from memory that is close to the GPU cores, so like in the actual GPU. That is typically referred to as VRAM or video memory. Again, if we want to load something into VRAM, we do have to ultimately get it from a disk drive. So this is just the framework where we haven't even really factored networking in. And the takeaway I want to really impress is that as data gets further away, like as in like physically further away from a processing core, it takes more time to actually, access that data if it's needed for one of our instructions. So we can run into bottlenecks, all sort of sections of this, like we could maybe be stuck waiting for memory to transfer from our, disk drive to the RAM. Or perhaps we have like no more space in our RAM. So we're, just have to, perform our computations and then spend a long time loading that data in. Maybe we are waiting for the CPU to send instructions to the GPU to transfer data from the CPU RAM to the VRAM. And you see it's getting pretty messy. Moving to a slightly more Zen table, we can think about the amount of time it takes to access data from a particular location where we've sort of normalized a single CPU cycle to 1 second, like human time. So at 3 gigahertz, so that's 3 gigahertz of cycles per second. We're taking a 0.3 nanoseconds a second for an instruction, and we're saying that's 1 second. So for a CPU core to access data that's stored in the cache, it's equivalent to waiting about 2 seconds to 1 minute. If you want to take data from RAM, that's 3 minutes to about 5 minutes. By the time we're getting data to disk, it's equivalent to, a 2-hour wait or a 2-day wait. Gets worse if we go to a hard disk drive, 11 days to 4 months. And if we want to access data from another supercomputing node, that's an equivalent latency, an equivalent wait of 3 to 30 years, so on the order of decades. So, this parallelism does not come for free. And depending on the sort of work that you're doing, your process is going to be constrained at some point. And there are a few sort of key ways that can occur. So your work could be IO bound, so in-out bound. And in that case, progress depends on the speed of input or output between your RAM and disk storage. Your work could be memory bound. So your compute time depends on the amount of memory that is available to hold your working data. So it's very common in machine learning where your video memory limits the size of training batch set. Sorry, it limits your batch size during training. Or you could be processor bound. So basically progress is limited by the speed at which the processor and the CPU or GPU can actually crunch through data and instructions. Out of the three, IO bound is the worst case scenario, and there's almost never an excuse for your work to be significantly IO bound throughout that process. So there's usually some way to mitigate that. Sometimes being memory bound, that's unavoidable. And you have a large training set and you only have so much VRAM. Best case scenario is being processor bound though, because that implies, right, that we're getting data and instructions to our GPU or CPU as fast as it can handle it. And in theory, you're getting something closer to the optimal performance, speaking very, very broadly. We'll go through a couple case studies subsequently where we'll kind of explore how this might apply to an internship project. David, do you have anything to add? Cool. Emily?
So I guess I might jump in there quickly. So I know it was asked on Tuesday, someone brought up with Chris whether you might ever be in a situation where you're using, say, Photonics, and you use, I don't know, say 3 nodes, but you're not using all of the cores on those nodes. So this is one of those cases where you might find your memory bound. So that is something to be mindful of when you're working with these supercomputers. And sometimes there's nothing you can do about that. Sometimes the best case scenario is using half the cores on a node and making use of all the memory. So just to put that in a bit of a context of some of your projects, that's one of the cases where you might run into memory bound cases with your work.
That's a great example. Thanks, Emily. Yeah, like if you stuck with using a single node, right? Like the number of core, like at the maximum number of cores you needed, but a smaller amount of RAM, you would be IO bound. So you'd be like waiting for that load time, the transferring from disk to RAM, which, looking at this table, horrible situation to be stuck in. You're not really kind of gonna be seeing close to the amount of performance you could if you had the enough available RAM. So thanks, that's a perfect example. So our case study. Going to try drawing on the screen again. So we have our intern Alice, and Alice is working on an astrophysics project. And she's looking at how photons, so individual particles of light, how they're scattered in the atmosphere of stars. And the actual algorithm that she's using to simulate this process is this thing called Monte Carlo simulation, where essentially we're getting the path of getting a single photon, and we're just simulating its path through this atmosphere until it escapes. And the idea is that, if we repeat this process enough times using, random variables to, random numbers to sort of account for all of the different possible interactions it can have, we'll, eventually arrive at some sort of understanding of like the average performance, density, say, of energy in that atmosphere. Now, in this case, each individual photon is its own simulation task. So, she addresses, she approaches a problem by chunking all of the thousands and thousands of simulation repeats across different distributed memory, different instances of the program. So, this is a case of distributed memory parallelism being applied to an embarrassingly parallel task. Now, if she was to write each of the, write her results to disk after each simulation, it's almost certain that her process would become I/O bound. So to mitigate this, she simulates, the entire chunk, just storing that data in an array or a list, and then writes these results in these chunks. The idea being that by balancing out those write operations into these larger chunks ensures that we're spending as much time as possible actually computing, the simulations for the photons. Now, for our second example, we have Bob, who's working on a computer vision project and is tasked with training a neural network on a very large data set of images. And working on Topaz, he finds that he's memory bound because he can only fit a small fraction of the data set into the VRAM of a GPU. All these images, and can only get some small chunk into VRAM. To address this, he could use this Python package called horovod. And what that will allow him to do is spin up 2 GPUs and they each get given their own sort of chunk of the data set, or a partition of the data set. That can actually fit within the VRAM, or enough of it can. And then these 2 GPUs, they'll train his model and after a certain number of epochs, average the weights to get the final model. So here we actually have sort of two modes of parallelism going on at the same time. So the GPUs, right? The GPUs, that's an instance of shared memory parallelism, but the data parallelism, so the breaking up the data set into chunks, here we're actually leveraging distributed memory parallelism. This would be a pretty typical way to kind of get extra performance on something like Topaz. So Kevin asks, how can you tell where a bottleneck occurs? Sometimes you can tell just by, or have a reasonable understanding just by looking at your code. You know, like if you're some Python code performing a write operation inside of a loop, and you can see that that's being computed hundreds and hundreds of times by each core, you can kind of reasonably assume that it's memory bound. Correct that and run a test to see if that's improved. There are also benchmarking applications for GPU or CPU-based programs that can show you whether or not your program is, you know, memory, IO, or processor bound. And in a couple weeks, you know, we'll be holding a session actually on profiling and optimization. We'll explore some of those tools. But to start off, you know, a really good starting point is just to think about the pattern, right, of data transfer and communication in your you know, particular pipeline or program, and to run a few benchmarks where you kind of like change, say, the batch size or change the number of processing cores to kind of get a feel for how your software performs. Helen asks, so this would be for Alice's case, doesn't that mean you also have to implement a queuing paradigm or process and keep track of which seeds belongs to which process? Yes, that's true, Helen. So there's a few things you could do in that instance. So you spin up all of your processes with MPI, and each MPI process has a unique ID. And you could use that perhaps to seed the random number generator of each of your individual processes. So you're sure that, you know, all of the simulations are, you know, equally pseudo-random. And in fact, next week we'll be holding a workshop on using MPI in Python. We'll be running through how you could do just that. Aiden asks, is MPI a standard implemented by multiple languages? That is correct. It is, the MPI standard is developed and maintained by the MPI forum, and then you have implementations of MPI. And the most commonly used ones are Open MPI and MPI CH. They are very similar. They implement most of the MPI standard. You'll only ever see some difference if you are looking at using a feature of like the most recent revision of the MPI standard. For the machine learning example, is it possible to average gradients instead of weight for each training iteration using Horovod? I suspect so. I would have to check, but I'm not a a daily user, right, of Horovod, but I believe that is supported. David, do you have any experience there?
Maybe. Is there like a cross correlation?
Horovod, yes.
The new and the old below the fold?
You might.
And
You can
the
average the
places,
gradient,
or
but there might be some
something
you
where
might get some more vanishing gradient issues. So it would depend on the specifics of your model.
not fine, but
Sorry, who was that chiming in? Please go ahead.
I think that was me. Just didn't hear properly. It's all good.
Oh, good. So essentially, likely.
Yeah. Yeah, the answer is yes. Horovod does support gradient averaging, but you just need to be careful that you don't encounter faster vanishing gradients.
well, I was thinking
And there's a few other edge cases depending on the structure and what your model's actually doing. So it would actually depend on the maths in that case whether you'd want to do it.
Thanks, David. Brittany asks, for tasks like running hundreds of large genome data sets using the same algorithm on Nimbus, would this be a memory-bound process due to shared memory parallelism? All threads share the same memory. Good question. So that it really actually depends on how long it takes for you to compute or perform the operations that you're interested in on each of the genomes. Now, given that genome data is pretty large, and you're just working on a workstation essentially with shared memory, I think you'll quite easily be doing tasks that are processor bound. So you'll be getting more data to your CPUs than they can crunch through, which is a good situation to be in. Cool. Does Sonic support C++? Yes, Sonic supports C++, has all of the sort of common compilers that you would expect. C++ and Fortran are perhaps the two most commonly used compiled languages in HPC, and I would eat my hat if a system wasn't set up to compile them. So good question. And yeah, it's something you can more or less rely on. So a question that I know I had at the start of my project, and yeah, it's sat around for a fair while, is like, how do I actually know how many cores or GPUs to request, or how much memory should I request to run my project or run my project? And unfortunately, there is no silver bullet for answering this. You have to run some test programs to get a feel for how your particular program or process runs and scales. And that can feel a bit frustrating at the start of your project. You're very keen to just start getting results, but it's really worth setting aside like a day or so to get some data so you can make an informed decision, because it can make a huge difference over your project, right? If you're requesting too many processes, right, you could be getting worse than like single CPU core performance. If you don't see how your machine learning pipeline, scales with multiple GPUs. Maybe you're using 2 GPUs, but that's actually slowing you down. Or, maybe you're training and it's running faster than it does on your laptop, but actually what's happening is it's training on the CPUs of a Sonic system, and because there's 128 cores available, right, you'll see a speed up compared to your laptop, but that'll still be orders of magnitude lower than you would get with the GPU. So if you don't perform these tests, you don't catch those little pitfalls, and you can't make an informed choice. Ultimately, the best allocation request will be a balance between the speed up and the cost in terms of your node hours or service units. So here's an example that's actually included with the application for Pawsey projects, where they ask you to provide some benchmarking data if you're already working on Pawsey systems. And we can see for this process, right, starting with, we have 128 cores, 8 nodes, got this wall time of 11.2 hours. So that's the time taken for the process to finish running as read from the perspective of a clock on the wall. And our cost in node hours or service units is 90. The optimal configuration from these tests is actually 64 nodes that gives us a wall time of an hour with an overall cost of 64. And after this point, as we add cores, as we increase cores, we actually, even though we're seeing a decrease in wall time, we're actually seeing a proportional increase in the cost. So like we're hitting a point where the additional resources are not efficient from the perspective of cost versus speed up. You don't have to run a comprehensive suite of tests. At minimum, I would say, like if you want to use multiple GPUs, you run a benchmark on one, run a benchmark on two, at least. If you're working on Cetonics, try running on at least, I'd like to sort of try to run on at least 4 nodes, see the performance going from 1 to 2 to 4. If you're seeing a really great speed up at that point, maybe keep on going. But at least 3 data points, right, to make an informed choice. If you're working on a Nimbus instance or a workstation or some other like personal machine, the ideal configuration will just be the one that gets your work done fastest. So if you're using MPI or OpenMP, even on your own machine, you can choose the number of parallel processors. It might be the case that choosing to run something on all of your CPU cores is the best choice for you, even though the efficiency, right, diminishes after that point. But like, you're not being billed for that. And if you're not running anything else on your instance, well, that's the best choice for you. But it's still worth benchmarking. So, single threaded 2, 4, 8, 16 cores, just to make sure you haven't landed in some region where you're actually getting, worse than single threaded performance or worse than, 2 core performance. Wouldn't node hours always be minimized with 0 parallelism? Interesting question. So if we're able to break down our problem sufficiently, like there's data parallelism, right? So we have some step that's dependent on a result from our data set. Now, if we can parallelize that process, we have all these other sort of like run-on effects in terms of like, cache locality or, the amount of memory available to us and all of the distributed nodes and so on. That all results in us actually seeing a speed up that is greater than the cost, right? The proportional increase in cost. At some point, that won't be the case, but in general, that's what we hope to see. The particulars of it get a little, it's a little complex, I guess, for just a general discussion without digging into some actual parallel algorithms. But for now, and we can talk about it more later, be confident that if we've thought about everything carefully, we can see a good sort of cost benefit return for our increased usage of parallel resources. Yeah, and it's, well, sort of. Even just requesting more CPU cores on the same node, that can give you a good parallel return. It might even be better, right, than multiple nodes. But it's a good point. So Aidan's mentioned like nodes are different to CPUs, and like that's element as well. Like Emily spoke earlier about being able to access RAM, extra RAM through nodes. So yeah, that would be an instance where we're really taking advantage of the fact that they're almost like their own little, their own computer essentially in the cluster. How much memory is on each node? Now, that is a good question. I think on Cetonics, we've got 256 gigabytes of RAM. Cool. Thanks, Emily. It's a big increase from Magnus, where we just had 64 gigabytes. Cool. So we'll be moving on from parallelism to talk about containers, which are a quality of life thing on remote systems and supercomputers, and then closing the session by talking about how we should manage and manage our data over the lifespan of our projects. But I think this is a great time for us to have a quick break. So I'll see everyone here at 10:55. All right, I hope we've all had a second to collect ourselves. So in this section, I just wanted to re-emphasize a topic that was mentioned yesterday, and something that will be probably quite useful for a lot of projects, and that's the use of containers. So just to refresh, so like a container is something that can package or contain all of the programs and other elements like your operating systems, needed to run some sort of program in. How's my audio? Cool. Bluetooth headset just had a bit of a connection issue just then. Great. Okay, so I was saying, containers, packages that contain all of the elements that we need to run a process or program in any computing environment. So this allows you to take code or a Python script that you've written on your computer or a workstation, and then transfer that to like Nimbus or an instance on Topaz or Sotonix, and then run it with very minimal or like no change to your code. They're also really useful from the standpoint of research, in that they allow us to reproduce results that depend on specific software versions. So this is very common in machine learning, where you have like a model that it depends on a particular TensorFlow version or a particular scikit-learn version. So if you define and create a container for your project, well, that container can be used at any point in the future to reproduce your results or use that model. Very loosely speaking, you can think of, well, when you think of an operating system, right? It consists of a kernel. So that's the part of the operating system that's responsible for, handling all of the actual device operations, like your storage or input and output, drivers, that sort of thing. And then over that, you have all of the programs and packages that the user interacts with. So that's like everything from like a command line interface to like your actual like desktop, like the Windows desktop environment or Linux desktop environment, the Mac OS Finder. Now, a container is a way of replacing the sort of user accessible portion of an operating system with that of another operating system, while kind of like keeping the sharing the same sort of kernel. And in doing that, you wind up with a scenario where the overhead associated with using a container is quite minimal, because it's essentially like you're just running a different operating system on the same hardware. So like from that, emphasize that if you're running a container, right, you wind up with this environment where all of the programs, environment, variables, and software are like controlled by you and installed by you. There is, though, a performance overhead associated with using a container, because some work has to occur, right, to perform the switching and get your program interfacing with the host system. But for like short to medium term projects, like an internship, like the time that they can save in troubleshooting is well worth the trade-off. So it's a little bit of an adoption hump because you have to learn how to use them, but they can save days. in troubleshooting if you're able to build and make use of a container. The platform that is used on Pawsey systems for containers is called Singularity, and it was specifically sort of developed for HPC applications. So you might also hear about Docker. Docker is used more often in sort of cloud compute scenarios. Singularity is more common on clusters. And a Singularity container that's like built on your laptop, you should be able to run in most of the world's HPC clusters. If using a container is something you're interested in, I think might be helpful. Popped a few useful links here. So we've got using containers on Pawsey systems, so the use with Singularity. And also there's actually a collection of Pawsey provided container images that you can use as a starting point for your own container. So like a container image that's designed for like GPU based applications, or designed for TensorFlow, or designed for an MPI with Python. And the Singularity Quick Start Guide is also very helpful. And myself, David, and Emily would be happy to chat with you as well about it and help you set up a container if that's something you're interested in doing. And you might ask, who should use a container? Basically, if you're doing a machine learning project and you can't, and you encounter any sort of versioning issues on Topaz, probably best to just use a container. Again, like machine learning pipelines tend to depend on a lot of different modules and specific versions of those Python modules or backends, and it just makes your life so much easier if you can define a container, upload it, and then just start working. The same with complex data processing pipelines, and just more generally anything where you have a large amount of software dependencies that aren't natively supported by natively supported on Sotonix or Topaz. So you just can't you're not able to just module load them. If you're working on a longer term project, it can be nice to set everything up on bare metal, but for the internship, the setup, ease of setup is well worth the slight trade-off into performance in our experience. And chat. Good, great. So our final section, managing data. Something that often catches new users on a Pawsey supercomputing system, or is that the storage provided by Pawsey is actually shared between systems. So it's typically the case, right? So historically, if you logged onto Magnus or you logged onto Topaz, you're actually accessing the same file system. And furthermore, unlike say Windows, right, where if you have a disk drive that you install, you'll see a separate device in Explorer that you kind of click on and you're in that drive. In Linux, like Unix-like operating systems, right, they operate from everything as a file paradigm. So basically, you'll have a folder in your file system that is actually like a path to that particular storage device. So on Topaz, you might be able to see home, scratch, and group, and they're actually three distinct storage areas that you have access to. Home, so that's the place where you can store software configuration files that can't be easily located elsewhere, and generally nothing else, because the space there is quite limited, storage is relatively slow. Then you have Scratch, which is used to store large amounts of data that are being actively queued and like or running on a supercomputer. And then you have group. So that's where you would, store software, Slurm batch scripts, and data sets that you need to use frequently. On Photonics, it's a little different. So with this new system, we have a new file system that's been introduced that eventually will be used by both, Topaz and Photonics. But at the moment, Photonics has its own home and scratch storage, and also software storage partition, which is, sort of replaces group. On Photonics, we're not really meant to use and can't really use either software or scratch to store programs and data in the long term. In particular, Scratch, which is the fast storage and also the largest amount of storage that you have access to, so 1 petabyte per group by default, that's actually purged every 30 days, or more so. Anything that you have on Scratch that hasn't been accessed or used within 30 days will be automatically deleted. So it's really important to back up your work or get your data off Scratch as soon as possible. So once you've finished working for the day, it needs to go elsewhere. Software, now that's used specifically, should be used to store software, maybe smaller data sets and batch or SBatch scripts. And that's only 256 gigabytes per project. And home, it's a little larger than actually the home on the Topaz file system, but it's only 1 gigabyte. So again, should not install software to home. Don't run projects from home, and in general, your first sort of act after logging in to Photonics would be changing to either your software or Scratch directory where you're actually working. So group, that's a particular name assigned to storage on Topaz. And by group, they're actually referring to like research group or project. So under it, you would see the various project IDs, all of the current Pawsey projects. The other storage that you have access to as a Topaz user, Photonics user, Nimbus user, pretty much anyone with a Pawsey account, is the Acacia object storage. So this is high-speed object storage for hosting research data, and it's going to replace group on Topaz in the near future. Acacia is a type of object storage, and it's used to store data that needs to be stored for longer than a few weeks, and it will be available for the duration of your project. So if you have an internship specific project, that'll be, this is the 10 weeks of your internship. If you're working on an existing allocation, it'll be for however long that group has that particular allocation. And there are 2 types of account associated with Acacia for each user. So that'll be, user storage and also project storage. And in general, you would want to be using your project storage because by default, there's 1 terabyte of that available to your project, whereas you only have 100 gigabytes allocated to each individual user. And Acacia, so just for a bit of context, it's built on this open source software named Ceph, where instead of files, your data is stored as objects in buckets. So instead of a scenario where we have, a hierarchical file system used to seeing, it's basically a bunch of buckets which have labels. and then data that is stored inside that bucket. So it's almost like a two-level system. And unlike folders, so you can't nest them, and you also can't change the contents of a bucket. To do that, you'd actually have to transfer the data stored in your bucket to Scratch or software, perform the computations that you're interested in doing, and then transfer it back to Acacia. Now, using Acacia, it's an important part of, your data workflow on, Pawsey systems, especially if you're using Photonics, because if you're just using software to store all of your data, you may very well run out of space. And then if you're storing all of your work on Scratch, you'll probably lose some very important file, right? Some file that hasn't been accessed for a month, halfway through your project, and you'll get no sympathy from the help desk, right? Because we're trying to, them and us here are trying to really make sure that Scratch is purged, the files will be deleted, and you have to back up using Acacia. Because it's new relatively, we'll be checking in with everyone to see how you're going using Acacia storage over the next couple of weeks, and making sure everybody's up to speed and supported there, before you're running into that. But just know there's a real reason to pay attention, I guess. Now, the Acacia user guide in the Pawsey documentation has all of the information that you'd need to get started. And there's also a recording of the Acacia Object Storage Workshop. It's available on the Pawsey YouTube channel and linked in the website here. But just very briefly, Pawsey supports the MinIO client for working with the Acacia file system. And this client can be installed also on Linux, Mac OS, and Windows. So you could actually install this on your own machine to access data that's stored in Acacia, your allocation. And you would also install this in Nimbus, right, to access with your Acacia data storage. The starting point of using Acacia is actually creating an access key through, portal.pawsey.org.au. And you'd log in to this site using your Pawsey username and password. Following if you just can follow the getting started instructions in the Acacia user guide, you'll eventually see basically a command that you can copy and paste into your Photonics session or Nimbus session that will set everything up for you. It'll set up data access for you. And so that process is actually, I found, quite straightforward, because they've gone to the effort to just give us a command to copy and paste. Once you have access to your storage, the commands that you'd need really are, so MC, MB to make a bucket, so alias, that'll typically be your project ID, and then bucket name, that's the name you want to give the bucket. And then similarly, if you want to delete the bucket, same pattern, except RB for remove bucket. And we can also do things like list all of the buckets that are associated with your project or account, or, upload to a bucket. So MC copy, right? Like the Unix command, source, it should be a slash there, target, and then similarly to download, source, target. And yeah, so this session's gone over a little, so I won't run through some examples, but what we will do is check in with you next week to see if you have any questions about using Acacia storage, and we're happy to, run another session or, record instructional videos or whatever it is we could do to kind of help you use Acacia. And yeah, with that, the end of the session. If you have any questions about this portion of the workshop, feel free to come and ask me at the end of the workshops today. Thanks, everyone. I'll now hand you over to Emily.
Wonderful. Thank you, Edric. Hopefully everyone can hear me okay. Yeah.